Hi everybody. It's been a while since I posted a video, and they are going to be a little more slower coming in the future here. We have a lot of big projects going on. We just finished installing a CAT scanner at work at one site, and we have end of the year things coming up. Everybody needs their inspections done and so forth before the year closes out. So I'm going to be a little bit busy with that, so I'm not going to have a lot of time to work on the audio things because it's just a hobby. So I hope you'll be patient and waiting for the videos to come out. Now this one's very interesting. We ran into a lot of problems troubleshooting and getting this amplifier module to work. I'll show you over here. It's up and running now. Works really well, but it was quite a journey, and as you would know, part of it was my own fault. You know what they say, show me where you've been and I'll show you where the problem is. And you'll see an example of that in this video. But for the most part, it worked out really well, and we got a few ideas of some different transistors to substitute because of the availability problems, and I'll talk about it in the video. And I think a lot of the clips that I did, I don't remember because they've been done over the period of about a month or so. So I don't remember everything I recorded, but we'll put some notes like we normally do up on the screen, some annotations. Some of you say that you can't read them because they flash up too fast. I have to remind you, hit the space bar or touch the screen and pause the video so you can read it, and then start the video back up if you can't read the comment. So with that said, let's get to the video, and we'll see you again real soon. Well, now, it appears as if we have a new first place winner for the worst speaker protect relay I've ever seen. Here's the cover, and here's the relay. Now, I don't know. That looks actually welded on there. My goodness. These were bifurcated contacts, as you can see. But, well, that didn't seem to help much now, did it? Wow. So as you can see from this relay, even though it has the bifurcated contacts, and you can see this is a good example. You can see these two are together and these two are together. So there's really only two sets of contacts, even though there's four little fingers there. And the whole idea is this big one comes in before the little one, just the way they're spaced out, just ever so slightly different. And what's supposed to happen is when this pulls in, this will actually take the arc flash, the larger contact. The smaller contact is usually like a silver or gold plated contact, and it is very low resistance. And its whole purpose in life is to make a solid connection with very low resistance, and when it comes out, it will actually release before this one does. You can almost see it. This side actually still works. You can see that little, I don't know if you can see down in there. And that's the whole idea of how these work. Now, of course, that didn't help us here. It actually melted this whole side off right here and welded, just arc welded this whole thing together into a big ball of metal. So this had to have been an incredibly terrible short when this happened. And you can see what that'll do. So what we've replaced it with, and I do have some of those bifurcated relays, but I don't have one in a 24-volt coil. They're very hard to get. You usually have to order them. Takes 7 to 9 weeks back order usually to order them from Mouser or DigiKey if you're lucky. I did find some from another source and ordered some, but they're not in. They're back ordered, but I got a lot better pricing on them than at Mouser's and DigiKey. So if they come in time for this project to be finished, I'll replace this with the bifurcated version. If not, we're going to use these here, and these are very heavy duty. I mean, where are these contacts rated at 12 amps at 240 volts AC? So I think we'll be okay. I know I've said this on many of my other videos, so some of you who watch my videos regularly, this is total repeat. But for those of you who don't, the thing that will kill these the most is turning the amplifier on with the volume control turned way up. Because think about it, when the volume is way up, you're already applying a high signal to that amplifier and there's no load on it. Once this circuit times out and these contacts close, they're going to close and they're going to dump all that high voltage across that low impedance speaker load. Your speaker is only, a few ohms. For instance, an 8 ohm speaker, the DC resistance is probably going to be closer to 4 or 6 ohms. So all that voltage of that high volume is just going right through these relay contacts and being switched. And it will cause quite an arc flash there. Conversely, when you turn the power off, same thing. Ultimately, you would want to turn the volume down on your amplifier before you shut the power off on your amplifier. That way, the only time you'll be switching a high load is if you actually have an overload. And if you have 1 or 2 arc flashes on these, it won't wear them out or tarnish them that much. It can handle it. It's just that continuous arcing and arcing and arcing that'll wear these out in short order. So it's just something to remember. Take care of your equipment. That's the key to it. Make sure the volume is down anytime you turn your amplifier on or off, and you'll see that this will last a lot longer. All right, let's put it together. We'll look at the schematic here real quick, and then we'll get the 2 boards in, and we're going to test the power supplies on this amplifier. But let's do a quick little rundown on the theory on this. This is a very common type circuit. I've gone over these. I actually did a speaker protect circuit video where we actually built one and we installed it and so forth in an amplifier. But same thing. You have your inputs from your channels. You can see your speaker leads, your gazintas and gazoutas, goes through this. You have your timing capacitor and your input filter and all that stuff. And then you have your Darlington or your pair here for driving this the coil here. So nothing out of the ordinary. This circuit actually right here will detect the peak. This really doesn't have anything to do with this circuit. And what these do is they will detect like a clipping situation or a peak situation when you're driving the amp really hard, and there is actually an LED, 2 LEDs, one for right and one for left channel, on the front panel of the amplifier, and they'll actually flash red when you hit the peak on this. We'll have to look at this a little more closely to see if this integrates itself into the actual overload protect circuit in the amplifier. I don't think it does. I think this is just for the purpose of flashing those lights, but I'm not sure. I could be wrong. I'll put a note up on the video if I find different. Again, I haven't really worked with this specific amplifier. I do know that it's, so far what I'm seeing, I'm loving the design. But let's get it put together so we can test our power supply out. Okay, our power supply board is back in and the meter is connected. And right now this top part is your positive regulated supply and this bottom is your negative. And let's just look at the schematic for a minute, because again, this is kind of a unique design. Let me move some things out of the way here. I know I get crabbed at because I don't put the camera or don't set the thing up properly so you could see it. So there you go. This is a pretty straightforward regulated power supply, and you only have one potentiometer, which is this one right here, and it adjusts and you can see it's limited by this Zener diode here. And you have your negative and positive, and they're both controlled by this adjustment right here. The transistors have been replaced with new ones, and I did leave the JFETs in there. They should be okay, and if they're not, then we will replace them as well. But I don't really want to try to find substitutes for those if I don't have to. I only have a few different styles of these JFETs, and I don't know if I have an exact match for them. Here are two diode packs. There's basically two diodes in each one. And if you look down here, these two little fuses, and you saw where I connected the two orange wires to this and the black wire to this, and you might think that that comes from the main power transformer, but it actually does not. Let me show you where it does come from. If you look in the back corner here, there's this other small transformer, and you can see the wires coming off of it, and it's also connected to the line matching taps, so you can this can be wired for 240 or for 120 volt mains or for 100 volt mains or whatever. And then it has two wires coming off of it, and you really can't see them very well, but they're down here. There's the two oranges and the black, and they come over and go in right there, and that's what comes in here and feeds this. So this whole power supply board has its own separate transformer for the regulated supply. Now, I don't know why they would do that. It doesn't make a whole lot of sense to me. They could have just as easily added another winding to this massive transformer right here and done away with the need for a second transformer, but for whatever reason, either this transformer already existed and they didn't want to have a custom one built, or they felt that maybe the line sag, which is a massive transformer for that, but you know, under heavy current, they didn't want the fluctuations of the transformer to show up on your regulated supply and somewhat modulated. Even though it's regulated, I don't think that would matter one lick. So I really don't know why that is, but this, again, this uses two transformers, and I believe, I'd have to think back and look at the video, but I think when we did that Sansui AUX1 amplifier, if I'm not mistaken, it had a great big toroidal transformer, I think, for the main power, you know, for the outputs, and then it had another smaller transformer that it used for regulated supplies as well. That might not be, I remember one other project we had on this bench where they did such a thing. So it's not unheard of, but it is kind of unique. Anyway, all of this has been replaced. We're going to power it up, and we're just going to see where we are. All right. So we're connected to the positive voltage. Let's turn it on. And I do have it on the dim bulb because I don't want, if something's wrong, I don't want it to kill everything. And you can see our bulb is nice and dim. And we're sitting just a little bit below 32 volts. We want 32 volts. And you can see here they're saying 32 volts here and minus 32.5 here. So we'll see if there's the big difference. So I don't see any problems with this. And I don't want to adjust it until we put full power to it. So let's put full power to it now. And look at that. Right on. Okay, so that's the positive supply. Let's look at the negative. They're both right on. So other than I don't see the discrepancy of that 0.5 volts, I don't think that matters either. But we have our plus and minus 32, so our regulated supply is good. I did hear the protect relay come in when I turned it on, and of course it will come in because it doesn't sense any DC on the speaker terminals, and the reason it's not sensing DC on the speaker terminals is because there is no amplifier board. So that's how this works. So when we shut this off, that drops out. That's what it should do. So I think we're in good shape. We have a good power supply. Now, the other thing is, I spoke with the owner, and he believes that it would be a good idea to replace these capacitors here. These may be still in very good condition, but like he said, anybody who would want to purchase something like this amplifier and would actually want to use it would want to buy something that has, you know, the main parts that could wear out, that have a shelf life on them, like capacitors, that they would want those to be replaced to future-proof it. Okay, as you can see, I fitted in the new capacitors, and they're a little bit different than the old ones if you look at them. Here's one of the old ones, and you notice the old ones had these solder tabs on them. The new ones had screw terminals, so we had to put screw terminal lugs on them, and that gave me the ability, or the opportunity I should say, to kind of clean up the wiring. So it's nice and neat now. We reused the old bleeder resistors. They were just fine. I tested each one of them. They were right on spec. So we just put them back in because I don't have any 2.2K 5-watt resistors like that. And I didn't want to place another order. Now, if you remember from the Marantz 250 series that we did, these amplifiers are notorious for very high inrush current because they don't have a soft start circuit or an inrush current limiting circuit. And I talked about this many times in other videos, and we've rebuilt the amps that do have them. We've rebuilt them before and kind of looked at what they do. And in the last one, what we did was we just did a simple circuit, just like Pioneer and Marantz and Sansui have done in the past, where you just have a relay and a resistor feeding the coil to the relay, and then you have a current limiting resistor in line with your power transformer. And when that voltage of the capacitor bank builds up to a certain level, then the drop across this resistor and across this coil gets to a point where it can pull the coil in, and this relay shorts out our inrush limiting resistor. And normally you need a pretty heavy resistor to handle that. Now, a lot of people talked about ICLs, or inrush current limiting modules, which are these little ICLs, thermistors, whatever you want to call them. They are a negative temperature coefficient resistor. So as the temperature increases, the resistance drops. So what ends up happening is, and did I say that right? Negative temperature coefficient, NTC? Yeah, I think so. But anyway, bottom line is, as current flows through them, they heat up, and the heat causes the resistance to drop, and then it kind of takes itself out of the circuit, as per se. It never really goes to 0 ohms. It goes to, you know, a fraction of an ohm, and that can vary depending on the model of ICL you use. And here's the problem. If you get an ICL that has a high enough resistance, cold resistance, to actually limit the current in an appreciable manner so it doesn't destroy your power switch, what happens is once it heats up, it still has residual resistance to it, and it will still continue to somewhat limit the current. If you have one that will drop down near to 0 ohms, or very, very low fractional ohms, either it doesn't have very much resistance at room temperature, or it gets very, very hot in order for that resistance to drop that low. And we don't want a lot of heat inside of our amplifier. So it always is a conundrum when you use these. That's why I said I hate using these in amplifiers. But if we use this just temporarily and then short it out, you know, bypass it with this relay, and this relay is good for 10 amps at 250 volts, by the way, then we can get the best of both worlds. And that's what we're doing right here. And what I really want to look at is when we turn the power onto this amplifier, there's going to be a huge amount of current flowing until the capacitors start getting up to their charge level. And that initial current is going to be very high. So this is going to limit it. Now, as it heats up, the resistance drops, but the current is also dropping because the capacitors are charging up. It's all kind of a balancing act. In the meantime, we have this little dropping resistor, and it is in series with the coil of this relay, and it's going across one of these capacitors to measure the capacitor's charge level. So when that capacitor gets charged to a certain level, this relay will come in and it will bypass this thermistor, or this ICL. And I talked about this and showed you a schematic. Go back and look at the, I actually did a separate video on inrush current limiting, or a soft start circuit. So go back and check that out. This is just kind of another iteration of it, and this is actually a board that I printed up. And just to make it look neater, kind of make it look a little more like it belongs there. Anyway, let's do some testing and see how our inrush current limiting circuit works. Okay, I have the oscilloscope set to trigger, and when we turn this on, we're going to see what happens. Here we go. And that's it. So let's take a look at what we're looking at here. The first thing I want to tell you is the way I am looking at this. This is your mains voltage going dropping across that inrush current limiter. And it is connected to mains, so you do not want your oscilloscope directly connected to mains. So in order to do that, what we're using is this little device here, and it is called a differential probe. This is an isolated probe, and it isolates the mains voltage from your oscilloscope. So the output of this is isolated from the input. Very important. Never connect your oscilloscope directly to mains. Bad idea. There's lots of videos on that, and I even did one on it. So anyway, you can see if we take the voltage, this ICL is, I believe it is a CL30. Yeah, CL-30. And what that means is at room temperature, it is somewhere between 2.5 and 2.7 ohms. And then as it heats up, the resistance drops. So if you look, our very first pulse here, when we first turned the amplifier on, you can see there's a negative going and a positive going, and I'm set to 20 volts per division, because this is a times 100 probe, and lots of math, huh? So just take my word for it. Each square represents 20 volts. So we have 20, 40, 60, a little over 60 volts. And if you take 60 volts divided by 2.7 ohms, because I measured this at room temperature is 2.7, you have about 22 amps of inrush current. So we're limiting the inrush current to this amplifier to 22 amps. Now, you can see how quickly it is heating up that inrush current limiter, because what you're seeing is A, the capacitors are charging up, and B, the resistance across that resistor, that ICL, is dropping. So when we get out to about the fourth pulse, you're just a little bit over 20 volts. Let's say 22, 23 volts. All right. So 23 volts divided by, let's say, 2 ohms. It's down to about 11 amps, or even less than that. So it's pretty low. And by the time the next one crosses over, the little relay, right about here is where the relay kicked in, right down about 5 volts or so. So what that's doing is, A, we have lower current going into our amplifier. We're not killing our power switch with real high current. And second of all, we're not switching that relay until the current is low enough that we're going to damage the contacts of the relay. So the contacts of our switch, the contacts of our relay, and the temperature of our ICL are all kind of working to protect one another. So this is going to mean, in a nutshell, that these components and our very hard to find, rare, valuable power switch are going to last a very, very long time. Now again, this CL30 would never be able to just remain in there without this relay shorting it out, because if you just left this in here, this only has a holding current of about maximum of 8 amps. So if you put more than 8 amps in it, it will burn up. It will destroy it. And there is an 8 amp fuse in this amplifier. Obviously it's going to run at 4 or 5 amps possibly. So this thing is going to be absolutely blistering hot. And eventually these crack and they wear out. They just don't like running at that kind of temperature all the time. So that's why I don't use these by themselves. And you have to have some way of shorting it out after it does its thing. The other thing is, if you turn the power off and then back on, this thing stays hot for a really long time. So unless you leave it off for like 5 minutes and let this totally cool down to room temperature, it's not going to limit the current when you turn it on the next time. So again, because this never gets a chance to get hot, because this shorts it out before it does, you can turn this off and in relatively short order turn it back on, and it'll continue to limit the current. The only thing you got to wait for is for the relay to drop out, and that will only drop out when the capacitors discharge. And the capacitors, if they're not fully discharged, this doesn't need to come out because they're already partially charged, and your charge current is not going to be as high. So it's a self-correcting problem, right? Okay, our power supply is now complete, and we're ready to start working on the amplifier. Well, now that we know we have a good power supply, let's get to work on the amplifier modules. And what I'm going to do is I'm going to just start out on the one that has the most damage to it. I'll move that out of the way. And you can see this is the one with the blown transistors, and the one transistor that's like totally missing. And I stand corrected on this. Of course, these emitter resistors do heat this metal plate, but also if you notice, these two transistors and these two transistors are also coupled to this plate. This is actually, over here, is all part of one big heat sink. And it is separate from the main heat sink for the outputs. And that's kind of strange that they're not coupling this to the temperature of these. And the only thing they're using for thermal tracking there is this transistor that they have kind of sitting off of the board like that. And when it goes in there, it kind of goes in between. You can see how it kind of rides down in there. But it doesn't really make contact with anything. So again, this is kind of a unique amplifier design, I have to say. But anyway, let's start replacing components, because this thing is just, I mean, it's bad. Well, we got the first board finished, and I do have a very limited supply of original 2SA 968s and 2SC 2238s. So I did use a set of those to replace these with originals. There are a few subs you could probably use, but they're not exactly the same as these. For these two right here, and just so you know, beside the capacitors, okay, so the capacitors were mostly okay, a couple of them were weak. All of these components are bad. These resistors, all these diodes, these transistors, you can see were blown. And for these, the 2SB 717, and I'm getting grease all over my fingers, and the 2SD 757, I replaced those with a set of Toshiba TTA 004s and TTC 004. These are really good replacements for these transistors. They're high frequency, they have pretty decent power ratings, and they have a very high voltage rating, so these are going to work perfectly for this. The capacitors on here, these are really nice caps. They're 105 degree caps. They are physically smaller than the other ones. If you here's the unrestored module. You can see how much bigger this one was, and they actually fold them over. And I think the reason for that was this amp sits like this when it's inside the chassis, and they probably did not want this hot resistor being right up against it like that. You know, heat convects up, heat rises. That's the only thing I could think of, because they have the same one here sticking up off the board, so I can't imagine it's a height problem. So I went ahead, since this one was so much smaller, I stood it up. We may have to change that when we go to install it, but we'll see. Now here's where things get a little bit interesting. All of these transistors were shot. These two were bad. This one was the one that was completely blown off the board. This one was shorted. These were shorted. These were shorted. The resistors were all blown. You could see the ones I had to replace in here. Had a few of them here we had to replace. But these ones over here are all still good, including this dual transistor package for the differential pair. And so I opted not to replace this and just put a new piece of heat shrink over it. I'm pretty sure they put the heat shrink on it to insulate it a little bit, to make it even more thermally stable. I'm just guessing that that's what they had from the factory. That's what I put back on there. I do have a limited supply of spares if I need this, but I think this is okay. As long as it doesn't have any shot noise in it when we go to test it, we're good. Well, as you can see by the previous owner, they marked these big X's on the top of these transistors. They're all shorted out. They're shorted really bad, all four of them. So for the NPNs, which is the 2SD 665s, we're going to replace those with these MJ21196s. And with the 2SB 845, which is the PNP, we're going to replace those with the MJ21195. So let's get these out, and we'll get the heatsink cleaned off. It's actually pretty clean, just has some dust on it. We'll dust it, and we'll get them all mounted up. Okay, the new transistors are in. You can just kind of barely see them there. And the module has been installed back into the amplifier. And I've got my dummy load connected to the speaker terminals. I have my meter set to millivolts to see if there's any DC offset. See if we can get a better view of that. Right there. And right now I only have just a small 40-watt bulb, so I am not going to expect the protect relay or anything to come in, but I just want to see if it even dims down at all. I want to make sure there's no shorts on this module because we did so much work on it. And if that looks good, we'll go to the next bulb, and then we'll see if we can pass a signal through it. And I'm not sure, I don't think this thing has automatic connector jacks for the preamp out and main amp in, so just for good measure I just put a set of jumpers on there. Again, I'm not sure. I just don't want to take any chances here. We'll see. So let's turn the power on and see what this bulb does. Okay, that's pretty bright, but it is dimming down. And again, this is a very low wattage bulb, so I don't think it's going to get much dimmer than that, and I don't think the voltage is going to get high enough to bring in the protect relay. But the good news is it dimmed down. So let's turn the power off. Let's go to a 100-watt bulb, and let's see what happens next. Okay, here we go. Oh, and that one dims right down. See that? Nice. All right, let's look at our protect relay. Hello. See if that comes in. Ooh, it came in. Okay. And we have about 20 millivolts of DC offset. That's not bad, and it's dropping. Okay, let's turn on the signal generator. And again, this bulb is probably going to get really bright. So let me shut this light off. You won't see as much reflection. That really doesn't help a lot, does it? How about here? That's better. Okay. All right, signal generator on, 1 kilohertz signal. Turn the volume up. And I have all kinds of crazy oscillation, but it goes away. Okay, of course the bulb is getting brighter, and that's what that oscillation probably is the that dim bulb that's in there. But that does concern me because most amplifiers will not oscillate even when they're on a dim bulb tester like that. So you can see, look at that. That's bad. So there is crazy oscillation in this, and that's probably what blew it up. I'm half inclined to go to the next size bulb and see if the oscillation goes away. It might be that just the voltage is just so low right now that the amp's not biasing properly, that I'm not checking the bias on the transistors. So let's do that. All right. Wow, that bulb doesn't even light up hardly at all. And let's see if we get, yep, protect relay. And as you can see, the big bulb there on the end, this one here, no light at all. So let's turn this up now and see what happens. Well, we're still getting that terrible oscillation. But you can see as you turn it up, it goes away somewhat. But that's bad. We can't have that. Okay, as you can see, I very precariously have the plug pulled out. And we're just going to look straight at the output of the preamp with no influence of the main amplifier. It's on. And look at that. Absolutely clean as can be. So, it's entirely possible that there's something wrong with those transistors at the front end of the amplifier, because I checked them statically, but I did not check them under signal. So there's something wrong in here still. We're going to have to go through and check all this and do a couple voltage checks, and that's going to be difficult. Now, this amplifier is extremely easy to work on like this, but not very easy to test in circuit because those wires are so tight under there, so we're going to have to figure something out. Okay, so I set this up and turn the amp on its side. You can kind of see everything's just kind of, yeah. Never mind, but I think I see the problem. As far as DC balance is concerned, that works perfectly. As far as bias is concerned, there is no bias voltage whatsoever on this. No matter which one of these 4 emitter resistors I check, I have basically no voltage whatsoever on them. And I think the problem is going to be on the bias circuit. And I haven't gone back and checked that yet, but we're going to see if that's the issue or not. But right now you can tell there's no bias on there. Of course, if I turn the volume up on the amplifier, you can see it goes right up. But so there is a drive signal, but basically the amplifier is running with massive crossover distortion, and that's what's causing that crazy oscillation. So the one thing I did not replace was the little bias transistor over here, and I did not remove this stabilizer, or this varistor, whatever you want to call it, I did not remove that and check it for its voltage drop. So one of these may have been damaged by when the thing blew up. I statically checked them with a with my fluke meter on diode check, but that's not always going to tell you the whole story when you start applying power to these things. So I'm going to have to remove this module, and I'm going to check this. I'm going to probably do a couple more little voltage checks here though first before I do that. Okay, looking across the stabilizer here, you can see I have 1.37 volt drop, and I think that's good for that. So that thing is probably good, and I'll show you what I'm looking across. That would be this right here is where we're looking. And there is a 1.3 volt drop across there. And it's saying right up here you should see about 1.2 volts. And so anyway, we're getting our voltage drop there. So now what I want to see is if I adjust this pot, will this voltage up here change? Okay, now I'm going to read at the output of R731 right up here, right there, that point. And we're going to see if this voltage changes when we adjust it. Now, according to this, we want it to be about 1.8 volts up there. And let's check it. You can see there it is. Let's see if we can adjust it now. Well, it doesn't do a whole heck of a... It jumps all over the place. You see that? Not very stable. Let's go to the other side of the resistor. It's at 5 volts. Let's see what happens when we adjust that. And you can see it's very stable there where we adjust it. So there's something going on with one of these transistors. So when I'm on one side of this 3.3K, I get a good adjustment, and that's like right here where it's 5 volts. But on this side, very, very unstable. Now these transistors tested good, and I think these are 706 and 707. I do not believe they got replaced. So we might have a problem with one of those, even though they tested good. These are ones that might, when they're under load, they're failing. Both of these diodes were bad. All of these diodes here were bad. They were all dead shorted, every single one of them. These were dead shorted. So we still may have some leaky transistors or some unstable transistors. I'm going to have to rebuild this part, is what it looks like. Okay, so I'm pulling my hair out, wondering why when I read in one direction on diode check, I get the normal diode drop on this varistor, but on reverse, even with this diode out and measuring on the pads, I'm still reading 3 point something volts of drop. So I started following the traces, and I followed this one right down here, and get a little pointer here. Followed it right down to here, which I removed this resistor here, and when I pulled the one leg of this resistor, it went away. Now tracing that all the way over here, it goes over to these two driver transistors. And I replaced these with TTA004B and TTC004B, which are really good replacements for the ones that were in there. However, here's what we found, if I can find the bad transistors. Where did they go? Of course, oh, here they are. So here's the old ones. Remember, they were the BD757, and I forget what the other one was. And the case is a little bit different, as you can see. But here's the big thing. Look at the pinout. Base, collector, emitter. These transistors are emitter, collector, base. So the emitter and base are swapped on this device. All standard transistors that we use today, especially like the Japanese ones that we're using today, are emitter collector base, not base collector emitter. I have these in backwards. Hold on a second. Yes, it is time to don my idiot boots. Now that the transistors are in the right way, we're good. And if we read this way, oh boy. the tangled web we weave, huh? Let's try this thing out now and see if it works. My big question is, how in the heck were we even able to get a signal to pass through this, even with that noise, with these transistors being the way they were? Pretty crazy, huh? Okay, after Tony put the transistors in the right way, everything is looking much better now. I have this turned on. We're connected across our resistors. This has been turned on and warmed up for a little while, and it's sitting pretty nice at 20 millivolts, which is where it should be. And I can adjust this down because we don't need that much heat on there. I think this is, I'm going to set this to only about 15 millivolts, maybe maximum. Very nice. And let's go up to our oscilloscope. We do have a signal fed into the preamp. These controls on this preamp are in bad shape. They're really going to need to be cleaned and adjusted and so forth. But there it is. Excellent. It's all fixed. So really the main problem that I chased my tail on was that when I replaced these two transistors here, the TTA and TTC 004s by Toshiba are wired backwards. The emitter and base are swapped on the pins. So this transistor had to be mounted face down. We can do that on these transistors because they don't have a metal tab or a heatsink tab. They're just plastic all the way around. And the original, like the 2SD 757, if you notice, these ones are, instead of emitter collector base, they're base collector emitter. So you really have to watch that stuff. And conversely, we would have had the same problem on this 2SA968 and the 2SC2238, but I had original replacements of those, and they were actually in very good, I had brand new ones, so they were the same pinout. But they also have the reverse leads. So any of the TIP series transistors, a lot of the KSC and KSA series, the two ends, they all have emitter collector base instead of base collector emitter. And so if you're going to replace the transistors on these, you have to remember that. And I think, if I'm not mistaken, I ran into that same problem on, I think it was the Sansui that I did. I think it might have even been the AUX1. It used some of these transistors in the same manner with the reverse leads like that. And if you remember, we had to go through and make sure we had that installed correctly. As we've been talking, bias has been holding very steady. So I'm going to say this amplifier module is repaired, and we're going to be ready to do the next one. The next module, the other module actually works. You can see, but it's very cruddy. Needs to be cleaned up. This glue has gotten all over everything, but it's all there. So we may not have to do a whole lot to this. Although you know my rule of making sure that I use the same semiconductors on each side, so I'll probably replace these two right here, and I may replace a couple of these small signal transistors, but other than that I'm going to leave this alone, other than recapping it, making sure all the transistors and diodes are good, because it's going to match that one over there. So this has been a long time coming, but I'm going to close this video out, and in the next one, tell me down in the comments section if you're interested. We'll do another soldering chat and we'll rebuild this board. If you're not interested in that, I'll just rebuild that board and we'll get straight to working on the front end of this and doing the preamp and all that. So, as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. And hopefully we'll have this thing working with both channels perfectly. Till then, take care. Bye-bye.